Hello everyone. Today I'll talk about solid mechanics at the AI-Robotics-Medicine Nexus. My name is Xuanhe Zhao from MIT. I'll focus on one example, magnetic soft robots. These soft robots are manipulated by external magnetic field that can do different types of operations inside a human body. Magnetic actuation has unique advantages such as remotely applied, untethered, safe to human body, and shielded by human body, and there are already existing infrastructures to generate such magnetic fields for the control and manipulation of magnetic robots. There are many previous groups working on this field. However, existing magnetic robots are based on relatively simple structures such as beams or simple domains such as single magnets. In 2018, we proposed this idea of printing ferromagnetic domain. The idea is you embed ferromagnetic particles in a soft material matrix such as an elastomer, and then couple an electromagnet around the nozzle of the 3D printer. Then as you print this ink out, you can reorient those ferromagnetic particles so that you can program the magnetic polarity of this fiber and then 2D sheets, 3D shapes. So you can program complicated shape and the magnetic domains of the materials you printed. Here is one example. So this is the alternating magnetic domain. Once you apply an external magnetic field, it quickly deforms into this M shape. You can see on the left-hand side is the model results, right-hand side is the experimental results. I'll discuss more details about the mechanics of the model. So the model is based on this ideal hard magnetic soft material model. The idea is the dipoles of polarized hard magnetic particles such as this neodymium ion boron particles has been saturated so that the permeability of this ferromagnetic particle is almost the same as the permeability of air and the polymer. Therefore, this hard magnetic soft material inside an applied magnetic field, they do not perturb this applied magnetic field, so that you can decouple the magnetic field and the deformation of this ideal hard magnetic soft materials. For example, you can calculate this applied magnetic field once in the domain and then save it as a field constants. Then you can calculate the deformation of your hard magnetic soft materials inside this applied magnetic field in a decoupled manner. So that's the advantage of this model. If you want to see details, take a look at these two papers and also Abacus code we provided. Then, based on this ideal hard magnetic soft materials, we can calculate the free energy of the magnetic field interaction with this hard magnetic soft material, the total free energy of the system, and then by doing derivative, you can calculate the elastic Cauchy stress and the magnetic Cauchy stress. So interestingly, once you have this magnetic dipole and applied magnetic field, the rotation of this hard magnetic soft material inside this domain even cause energy. And this magnetic Cauchy stress is also an asymmetric tensor. So there are some quite interesting mechanics behind this material. With that model, now we can calculate, you can see, accurately predict the deformation of this hard magnetic soft materials or ferromagnetic soft robots. So here is a beam you can see top is simulation results, bottom is experiment results, almost dead on with each other. Here is a more experiment and comparison between experiments and simulation. Then based on this, now you can use a model to guide the design of complicated objects. For example, 2D origami, right? You can see this complicated patterns of this ferromagnetic domain inside this origami. And 3D metamaterials of Auxetic structures. You can use model to guide design such a complicated Auxetic structures. We want to even explore the impact of this magnetic soft robots in the field of medicine. Especially, we want to treat acute stroke in the golden hour. So in United States, the stroke is number 1 cause of long-term disability, number 4 cause of death. Currently, right after stroke, doctors can use a guide wire to clear the blockage. However, there are lots of challenges with this method. So challenge number 1, unavailability of doctors in rural area. If the patient is around a medical center, then doctors may have enough time to treat the blockage. However, if the patients are in rural area, if you transport the patient from rural areas to medical centers, then you may lose the golden hour. So that's number 1, intrinsic challenge. Number 2, those heroic doctors who treat the patients, they receive accumulated radiation because they need to work under this X-ray to observe the location of the guide wire and the location of the blood vessels. So they receive accumulated radiation from X-ray. So these are the challenge. However, for the patient, time lost equal to brain lost, right? How do we address this? We propose the design of a tightly operated, even autonomous soft robots. The key idea is now you use this hard magnetic soft material to fabricate this guide wire, and then you apply external magnetic field so that this guide wire can bend on demand, navigating inside this very complex tortuous blood vessels in the brain to reach the lesion area of a stroke. Here is one example. You can see this is a magnetic guide wire. You apply external magnetic field so that it bends on demand. This guide wire now navigates inside a real size cerebrovascular phantom with simulated blood. Just to put it in perspective, these are the 3 locations of the aneurysm. You can see this guide wire can easily navigate around those areas and then navigate inside the blood vessels, complicated patterns of blood vessels in the brain. Now we can go even one step further. By high precision medical imaging, we can observe the location of the blood vessel and the location of the guide wire. Then we just need to solve an inverse problem. The inverse problem is what magnetic field we should apply in order to bend this magnetic guide wire along the desired trajectory to navigate along the blood vessel. So deep reinforced learning neural network is right suitable for such a complicated inverse problem. Now we're doing millions of simulations to feed them to this neural network, and then use neural network to suggest a control variable of this applied magnetic field to accomplish even autonomous control. So if you want to see details, take a look at the following paper. We can even think a little bit further, right? Now, AI plus 5C plus robotics, we believe this really present future medicine. So especially in the sector of minimally invasive surgery, scientists are all on board. Surgeons, they are also on board, so they can save more lives remotely. For patients, time lost equal to brain loss. So all the stakeholders are on board, behind this vision. So I want to acknowledge all collaborators and students.